I already mentioned I'm Mike Riddle. I'm Executive Vice President at Opgw America, and I've been working in the electric utility industry and fiber optic cables for nearly 30 years. And that's enough about me. You can look me up on LinkedIn if you would like to know more about me and my background. Today we're talking about optical ground wire, and just a quick reminder, the governing standard for optical ground wire is IEEE 1138, the 2009 edition. I serve on the IEEE subcommittee that's responsible for that standard, and it is under revision, and it's actually should be balloting soon. It's been completed. It's got to go through some editing and whatnot, and then it will be out for balloting. So we probably will have the 2020 edition of it coming out later this year. No real big changes in it. Some refinements. And just a reminder, the function of OPGW is twofold. First, it's replacing a shield wire on a transmission line. And a shield wire itself has two functions. First is to protect the phase conductors from lightning strikes and the resulting damage from them. And then second, it provides a path for fault current in the event of a fault. The secondary function is to add this telecommunications capability. In our day and age, however, it's interesting that sometimes the secondary function is of more interest and concern to people than the original primary purpose. In order for us to understand some of the concepts about optical ground wire design that will follow, I need to make sure that you recall some basics about fiber and loose tubes and how they work. Because this is really about OPGW design, I'm not going to dwell on fiber. I just want to hit the high points of it. The most common fiber used in our industry is low water peak single mode fiber. The governing standard is G652D, and an example of this fiber type is the Corning SMF28 family of fibers. Now, there are various world-class suppliers of standard low water peak single mode fiber. And an important takeaway is that while each company will have its reasons why it thinks its fiber is better than all the rest, the fact is that in the field, they're all generally splice compatible with one another. So for example, you can splice Corning SMF28 fiber with OFS all-wave fiber, no problem in the field. And you can easily go about 60 to 90 miles. Oops. Fiber itself could be and will be the subject of its own webinar. So today I just want to hit the one performance specification that's the most important one for users of OPGW, and that's attenuation. And attenuation is loss of power over distance, and it's expressed in dB per kilometer, or really dB per unit length. So you could use dB per foot, you could use dB per mile, you could use dB per furlong if you wanted to. And the concept applies regardless of which unit of distance you're using, and that is that you inject a certain amount of power at the transmission side of your optical link, and then over distance, the signal as received has less power in it, and that's expressed as dB loss. Now, when talking about those attenuation limits, you as a user, that's really important, and you really should have limits that you specify and hold the manufacturer to. Recommended limits, and these are good limits, doesn't matter who the cable is coming from. Any good company can meet these limits. Or that standard low water peak fiber that I mentioned is 0.34 dB per kilometer at a wavelength of 1310, 0.2 at 1550, and 0.22 at 1625. Now, these are the three most common wavelengths used within the utility industry, and of them, by far the most important is 1550. And it turns out that because fiber becomes more bend sensitive as wavelength increases, 1550 is really a good benchmark for your performance in general. So if a fiber is good at 1550, most of the time, like 99% of the time, it's going to also be good at 1310 and 1625. But it is possible, and in fact, I've experienced it, for a fiber to test okay at 1310, but not test okay at 1550. When you talk about these limits, they should be based on a bidirectional average of each and every fiber. What that means is that you are testing the fiber from both the inside end of the cable and the outside end of the cable, and then you average the results. The limit should apply to each and every fiber. Sometimes some suppliers will try to get you to accept an average across a reel. And first of all, there's just no reason to do that. And then second of all, it is theoretically possible that you could have one fiber with high attenuation such that you really can't use it. And so effectively you've lost two, right? You've got a transmission and a receiving on a different fiber. And that then means that you specified, for example, a 48 fiber cable and paid for it, but you actually received what to you is really a 46 fiber cable. And there's just no reason for that. Again, any good cable company can agree that each and every fiber in the cable will meet the limits that you have specified. And the limits need to apply to the finished cable, not just the bare fiber specs. And the reason that is that we buy the fiber and any cable company has to process the fiber. Traditionally, there were at least three steps. There was fiber coloring, fiber tubing, and then cabling. There can be more steps depending upon the cable design. And each of those steps, the attenuation could increase just a little bit. So if a manufacturer has processes that aren't state of the art, they could be increasing the attenuation significantly. And yet they could say that they still met your specification because you only gave the bare fiber specs. Again, it's in the category of there's no need for that. You can specify limits and you can have them apply to the finished cable, to each and every fiber, bidirectionally averaged, and any good cable company can agree to that. There are other types of fiber out there. Not going to talk about it in detail today. There's G654 fiber, which is kind of a new generation of fiber that's trying to combine the points of standard low water peak single mode fiber with some good features of non-zero dispersion shifted fiber. Talk about it on another day. There's also multi-mode fiber that comes at utilities from time to time, and if it does, please just let us know. We'll be glad to help you out. For today, I just want to focus on the standard low water peak single mode fiber. Moving on to loose tubes. Today, aerial cables such as Opgw and ADSS are overwhelmingly loose tube designs. And the loose tube design concept works by having the fibers laid in the tubes in a sinusoidal shape, as you see in this illustration here. And what that does is when the tube elongates, which it can do from either changes in temperature or changes in wind and ice loading, are even more pronounced, the tube will elongate and initially the fibers will just start to flatten out. So they don't experience any of the force that's on the tube until they get perfectly straight. That's what you see in the math over here. Now, an important concept about this is what's called in our industry excess fiber length. And that's the extra amount of fiber per unit length of tube or cable. It applies to both the tube and the finished cable. And as a general rule, you want as much excess fiber length as you can get. The excess fiber length directly relates to the zero fiber strain margin. And this is the point where the fibers begin to experience strain, and it's usually expressed in percentage of the rated breaking strength. So for example, if I told you that I had a cable design with a rated breaking strength of 20,000 pounds and a zero fiber strain margin of 50% rated breaking strength, you would then know that the fibers do not experience any tension until the tension on the cable is 10,000 pounds, 50% of the 20,000 pound rated breaking strength. Just a couple remarks almost as an aside before we continue. You can understand intuitively that for this concept to work, there has to be enough physical room in the tube for the fibers to have this shape. Beyond a certain point, the tube becomes overfilled and then the fibers lose the ability to move freely, and you've effectively undercut a benefit of the loose tube design concept. Another point that's important for you is that in the field, you have to distinguish the fibers one from another. And these days, most tubes used in OPGW have 24 fibers or more. So how do you distinguish them in the field? Well, there are two techniques. One is bundling or binder threads, synonymous terms. And what these are is you take a bundle of the 12 standard colors and you wrap a color-coded thread around them. So you begin with either the 12 standard colors with a blue thread around them and then an orange, repeat those 12 colors and an orange binder thread around it, and then so forth and so on. You can also use ring marking or band marking, again, synonymous terms, where you take the 12 colors and then you repeat them and you put a black ring mark on each fiber. In that system, you will have a blue fiber and then you have a blue fiber with a ring mark and an orange fiber and an orange fiber with a ring mark and so forth and so on. In theory, you might wonder about the black fiber. What do you do with it? And in theory, you would use like a white marker instead of black, because obviously black on black is not going to show up, or you might use yellow. But in reality, in production, that's not really so practical. So most suppliers will just leave the black fiber uncolored with the ring marking on it. And then a final note on this slide is that if you take a tube and you strand it, like you see in this picture, you increase that EFL because of the helix that's in the tube. So in the tube, you're typically getting about 0.25% excess fiber length. If you strand the tube, you typically get about 2.5%. And we'll see why this is important later. Today, in the world, there are basically three types of OPGW used, and they each have their advantages and their disadvantages. There is not one design that is overwhelmingly superior to the other. It really depends upon what you're doing with the cable. So those three design types are center tube designs. There are two flavors of center tube designs. You can have a plain tube in the center, or you can have a tube in the center with aluminum around it. But the concept is essentially the same. The tube with the fibers is in the center of the cable, and then there are wires stranded around it. The second type is aluminum pipe type design. This design type is actually the oldest of the three. In this design type, you have an aluminum pipe with plastic buffer tubes inside the center. Now they might be stranded around a center strength element as you see in this illustration, or they might not be. At InCab, we use the center strength element, but some others do not. And around that aluminum pipe, you strand wires around it. When you're stranding these wires, the overwhelmingly most common materials that are used are aluminum clad steel and aluminum alloy. And the sizes and how many you use of each type, that depends upon what the specific mechanical and electrical properties the designer is trying to achieve. So you've specified a fault current, which we will talk about later, and maybe a strength and whatever else you've specified, and the designer goes to work and will use those materials to meet your requirements. And the last type is the stranded design. The stranded design features a stainless steel loose tube that's been stranded around a center wire. That wire could be ACS as it's drawn in this picture, but it could also be aluminum alloy. Again, depends upon what the cable designer was trying to achieve. And you could use 1, 2, 3, or even more tubes, depending upon the fiber count and again, what the cable designer is trying to achieve. And yes, we will talk about the advantages and disadvantages of each. And we'll also talk about what is best practice for each design. So best practice in the industry, what goes into the best possible version of each of these design types. First up, center tube design. The advantages are that it's loose tube construction. Of course, all of these are really loose tube cable, but you'll see that loose tube means different things when it's actually applied. In this case, the disadvantage of center tube designs is that you have the lowest zero fiber strain margin of the 3 design types. The best you can get is about 40 to 50% of the rated breaking strength of the cable. And what that means is that these do have the potential for reduced reliability, especially if the fiber strain goes above 0.2%. So remember that tension on the fiber. So if the tension goes above 50% rated breaking strength, the fibers will have tension on them. That's expressed in percent of strain. Now, why might that happen? Well, because NESC Rule 250B allows the tension under fully loaded conditions to go up to 60% rated breaking strength. So you would have a time there in operation when under wind and ice loading, the fibers are actually experiencing tension. But under everyday conditions, the tension is probably around 15%, plus or minus 5% or so. And under everyday condition, then the fibers are not experiencing tension. So you're kind of playing a probability game, taking a little bit of a risk in order to get the advantages, which I've yet to talk about. Those advantages are that this design is mechanically and electrically very efficient. You get small diameters with good strength and good fault current. They're also very cost effective. And then I will tell you my bias. I come from a metal cables background, and I like the stainless steel tube. I think it provides better long-term protection for the fibers than using plastic, which we'll talk about in a minute. So consider these advantages against this disadvantage of you're taking a little bit more risk on your optical reliability. Now, some people, splice techs, don't like working with the stainless steel loose tube. It's perceived to be more difficult. I tell people it's not really more difficult. It's certainly not easier. It's just different, and you have to be shown how to do that. And the cable manufacturer always has a process that makes that that will teach you the proper way to do it. I think we have a really good one. These cables have lower flexibility and are more susceptible to being deformed or crushed during pull-in. So that's a significant disadvantage. Because of that, they do have significant pulling restrictions, and you do have to use an anti-rotation device and larger stringing blocks than you would otherwise. And you limit your fiber count to some extent. A lot of suppliers can only do 48. The most that I've seen and the most that we can do is 96 in this design type. What goes into the best possible version of a center tube design? Well, first, you need to maximize that excess fiber length. It turns out that you can kind of juice things up a little bit in your production process, but the best you can do is about 0.4%. If you're going to use aluminum around the center tube, you have two choices. You can take a stainless steel tube and insert it into an aluminum pipe, or you can clad the stainless steel tube with aluminum. We think that the cladding is better because you end up with an optical unit that acts as a single integrated element. When you're making that tube, you need to have inline EFL control. So you're ensuring that each and every fiber has exactly the same amount of sinusoidal shape in it. That's really important, again, for your long-term optical reliability. You also want to use eddy current testing to ensure that you have a 100% perfect tube. Eddy current testing is a commonly used technique in other industries, and it just is a way of checking to make sure that the weld is good and that there's no holes or voids in the tube. You also should use gel specifically formulated for use in laser welded stainless steel loose tubes. This gel, first of all, you can distinguish it from standard gel because it has a slight color to it. We use a gel that's a very light brown. There are some gels on the market that are very dark, but the point is they always have some color to it. Standard gel is just clear. This gel for use in stainless steel loose tubes has a higher temperature rating and it has higher hydrogen scavenging. So the fabrication process can impart hydrogen into the tube, and hydrogen and fiber don't get along. Now, all fiber has some protection against hydrogen in it, but we think it's better to go ahead and use the gel that has the higher hydrogen scavenging as extra insurance. When you're color coding the fibers, I talked about that before, and I mentioned there's bundling threads or ring marking. Well, you can actually do both, and splice techs like that. The bundling threads make it easy to separate the fibers into their groups. But if you're not careful, you can lose track of the bundling thread. And so ring marking gives you a backup if you lose track of a thread. Without the ring marking, then you basically have to start over. So you've lost time. So we like to do both. It's a little bit belt and suspenders, but it does have a benefit to the people in the field. And you need to be conservative with your wire lay length and preform so that you get good fit and a cable that's integrated. So you cut it and it doesn't just spring apart on you. These things are important for that kind of performance. Next up is the aluminum pipe type design. The advantages to it is that it's, again, loose tube construction, but better zero fiber strain margin than the center tube designs. You can get 50 to 60% rated breaking strength. That's about the best you can do, but you can at least cover fully through your NESC 250B rules. Now, beyond that, there are extreme wind and concurrent wind and ice loading conditions that could exceed this, so you're still potentially taking a risk. A lot of splice techs prefer the buffer tubes. Why? Because that's what they use for every other type of cable that's out there. Indoor cables, duct cables, ADSS is another cable with a plastic buffer tube. So they've done that a lot and they're very comfortable with it. Again, I think it's just a question of training but sometimes perception becomes reality. Another advantage is that the aluminum pipe has excellent electrical properties. You get really good fault current ratings using it. Oops. Disadvantages. I do think that the stainless steel loose tubes provide better long-term protection. That aluminum pipe is relatively inflexible and susceptible to being crushed or deformed during pull-in. And because of that, you always need an anti-rotation device with these types of cables. You have to use larger stringing blocks, and you've got pulling restrictions, how far you can go and how many angles you can pull through. There are some environments, and that includes here in Texas, where the aluminum pipe can corrode away. Here in Texas, it's because of buzzards landing on cables and pooping on them, and their poop is really acidic. This type of cable does have extra manufacturing steps, and that does mean it. Are we back? So picking up with the fully stranded design, again, loose tube construction, the highest zero fiber strain margin, and that means that you can meet NESC 250C and D rules, no problem. Again, I've talked about it, the stainless steel loose tubes provide good protection. This cable tends to be more flexible and crush resistant because if you look at the cross-sectional area, it's a lot like a conventional ACSR or other standard overhead conductor or cable that's used. It's more flexible and crush resistant, and because of that, you don't need an anti-rotation device during stringing. You can often go longer and through more angles, and that might enable you to eliminate some splice points and thereby save some money. But the disadvantages are that it's not as mechanically and electrically efficient. You see in the cross-sectional area, there are these little gaps, and no material means you get nothing electrically or mechanically. And so overall, the design is not quite as mechanically and electrically efficient as the other two. And you also have the disadvantage of crews not liking to work with the stainless steel loose tubes. What goes into the best practices of this design type? Well, a lot of it is like the center tube cables. You need the inline EFL control. You want to use the proper gel for it, the color-coded bundling threads and ring marking together. You want to be conservative in your wire lay length and preform for a good fit. In addition, you want to make the tubes slightly smaller than the wires that are around them. This way you get a kind of a bridge effect so that if there is a crushing force applied to the cable, such as the force you get just going over stringing blocks or the application of accessories, the entire cable has to be giving before the tube actually sees any of that force. I'm also now realizing that I think I forgot to do it here for the aluminum pipe type design. So I apologize for backtracking. What's the best possible version of that cable? Well, first is what plastic do you use? And PBT we think is good. It's durable and abrasion resistant. When you strand these plastic tubes, you should strand them using reverse oscillating lay, sometimes also called SZ stranding, with the conservative lay length. We also include both a thermal barrier and a water barrier the thermal barrier should be obvious. The cable will heat up if there's a fault or if there's a lightning strike. That helps protect your optical unit in the center of the cable. Water barrier, a little bit more subtle. If the tube is breached, the cable is going to fail optically. A water barrier, though, slows that process down considerably, and you should begin to see an increase in attenuation over time, an extended period of time, and therefore be able to plan and react accordingly, as opposed to it being a crisis on January 2nd at 3 o'clock in the morning during the middle of a snowstorm or something. Next up is your choice for how you make this pipe. You've got two choices. You can extrude the aluminum pipe or you can weld it. And it's my belief that the extrusion process is better for making this. It ensures that you have no weld defects or holes or voids or weld cracks that can develop. You get a perfect tube. Now, we talked about with the stainless steel tube using eddy current technology, but that's a ferromagnetic process, so that doesn't work with aluminum. Extrusion ensures that you get a perfect tube. Again, conservative wavelength and preform for a good fit. Okay, now we're back to where we should be. So, design parameters. So the most important parameters are the fiber count that you're trying to achieve, your diameter requirement, and your fault current capacity. Now these three all work against one another, right? Because as the fiber count goes up, the diameter has to go up too, but you're trying generally to minimize the diameter. Likewise, the fault current capacity goes up. As the fault current capacity goes up, your diameter requirement or your diameter is going to tend to go up as well. And you might have a situation where I can use the space to increase the fiber count, but I'm trying to still maintain a certain fault current. So again, they conflict with each other. You end up having to balance them. As I say here, there are significant trade-offs. The fiber count is ultimately limited by the tube size and your overall cable diameter. I think you can understand each tube has a maximum safe fiber count. And as I mentioned earlier, if you overfill a tube, that actually shows up in the cable specifications as a lower zero fiber strain margin. And good design, in contrast, you want to maximize that zero fiber strain margin, which in turn minimizes the fiber strain at the maximum rated design tension. The maximum rated design tension per the IEEE standard is the maximum tension that the cable manufacturer will allow their cable to be at under any design condition. So NESC heavy or the extreme wind or concurrent ice and wind loading conditions, you have to keep the tension as a cable designer less than what the manufacturer specifies the MRDT to be. If I put too many fibers in a tube, I will lower this number because I've lowered this number too. Tube size and pipe type cables, it's how much space do you have inside the tube. In stranded cables, it's how much space do you have around the wires. And in center tube cables, it tends to be how big of a tube can you make. Diameter, as I said earlier, the smaller the better in general, but you do have to be aware of the trade-offs. These are typical ranges for us and for other cablers too. The most common range is this, but in theory, I can do any size that you want. But again, consider the trade-offs. Larger diameters, in addition to increasing the cost of the cable, right? Because bigger diameter means more material, that means more cost, all else being equal. Bigger cables also put more loading on a structure, which can increase the cost of the structure. Plus, you're you end up shortening the maximum available reel length that the cable supplier can do, which in turn can mean more setups and splice points. And it could also increase the hardware cost too. So just be aware of these trade-offs that come with allowing the diameter to go up. Next up, fault current. For the user side, they're looking at this, and that's the fault current squared times the duration in seconds. Where does that come from? Well, ultimately, both numbers really come from your system planning department. So how much current is something that they can calculate, but there are two conditions that are used, single phase or three phase. Which do you use? Well, it's a function of your design philosophy. How much risk are you willing to take? Faults aren't really common, but they do happen. When they happen, there's a lot more single phase faults than there are three phase faults, but again, they do happen. Now, you can make an economic case that maybe worrying about a single phase fault condition is good enough 99% of the time. The difference between the two is not a factor of three, as you might originally think. It's more like a factor of two. But because the fault current is squared in this calculation, doubling it effectively increases the fault current capacity by a factor of 4, right? 2 squared. The higher this number, the more metal I have to have in the cable. I mean, that's basic physics. What about the duration? Well, that's your expected clearing time. And some utilities will consider only a single contingency. So a line trips out, that takes 4 to 6 cycles. So let's use 6, that would be 0.1. However, most relay and control schemes, in fact, all of them that I'm aware of, allow for one attempt at a reclose. There'll be 1 or 2 cycles with nothing. And then if the condition that prompted the fault is still there, there'll be another 4 to 6 cycles, and the line will trip out again. That intervening time period does not allow the cable to cool, so you can ignore it. And you can then say, well, I'll base my clearing time on the one attempt at a reclose and get 8 to 12 cycles. So now I'm up to 0.2 for this number. A more conservative approach is to consider failure of the primary system and that the fault is cleared by backup protection. Several decades ago, that would take about 30 cycles, and in fact, that's still a commonly used number. Today's relay and control equipment can easily do it in 22 cycles. Now, strictly speaking, I, as a cable designer, don't really care which you use. That's really your decision to get this number. I just want you to understand that the effect is the bigger this number, the bigger the cable has to be, and that's going to make it more expensive and all the other trade-offs that we talked about before. That then means it's a function of your design philosophy. You come up with this. I, as a cable designer, then go and work on actually meeting that requirement. And there are some important variables that you need to be aware of. And there's an underlying methodology. The methodology that we recommend you use is IEEE 738. In this methodology for a transient condition like a fault, there's the initial cable temperature and the final cable temperature, and that difference is the single most important variable in the calculation. So the two numbers that you pick are really critical. It's an initial cable temperature, not an air temperature. In the United States, for literally decades, that initial cable temperature was taken to be 40 degrees C, which is 104 F. And that was because it's a realistic cable temperature on a summer day, right? You go out and the air temperature might be 80, but you get in your car and your car feels like it's 100 because the metal in the car is picking up solar radiation, which is heating it up. Same thing happens to a cable. it'll be hotter than the air around it. The upper temperature limit, when I first started in the industry, 180 was used, and then it kind of bumped up and ended up on 210. Above about 210, you begin to have concerns about the performance of your optical unit, and you also have some concern about annealing any aluminum alloy wire that's used in the cable. Now, it doesn't contribute a lot of strength to the cable, but it does contribute some. And so if you anneal it, it becomes just dead weight, which, I mean, it's not really a good thing, may not be bad. Your cable might sag a little bit more, but to be safe, it's just better to stick with this. But you do have to think about how to define it. Some suppliers will apply it to the hottest part of the cable. And for a long time, that was the standard practice. And the hottest part of the cable is always going to be that aluminum alloy wire if it's there. Not the coolest part of the cable. That's generally the optical unit. And there could be as much as a 30°C difference between the two. So if manufacturer A uses 210, 40 to 210, but defines it at the hottest part of the cable, and manufacturer B uses 40 to 210, but applies it to the coolest part of the cable, they're effectively saying that the hottest part of the cable might be as much as 240, and you really can't make a valid comparison between the two designs. Just something to be aware of. You really should define this, what criteria you want used in the calculation, and make sure that the manufacturer sticks to it. Now, some people say, why can't I just say equivalent to 3/8 inch EHS or a 7No8 or some other conventional cable? And there's two reasons why that's not a good idea, in my opinion. First is it's too vague. You can't find a conductor manual that tells you what the fault current capacity is for 3/8 inch EHS. In fact, it's difficult to find good published data for the AC resistance, which is another important variable in that calculation. And what upper temperature unit do you use? In these conventional cables, there's no aluminum alloy or optical unit to worry about. So what do you use? Well, the second reason is if you nevertheless make some assumptions about these things, you'll still find that the ratings for these cables are really low. When you think about that further, that's not terribly surprising. These cables, like 3/8 inch and 7No8, became industry standards literally around 100 years ago. And there was much less demand on the power grid in the 1920s than there is in the year 2020. So sorry, you need to tough it out and work out the numbers. Hate to be the bearer of bad news. Now, at InCab, we believe that if you design well for fault current, then you're going to get good lightning performance too. Lightning performance has been a big topic of much discussion and controversy at the IEEE Fiber Optic Subcommittee. There's no agreed upon guidelines for lightning design. And the reason is that there's not enough data from the field to really allow you to work out what the guidelines ought to be. So you can only make some very general observations about lightning performance. The first of them is that size is important. So if I've got a cable design and I use a 2mm wire, and then I have another cable design and I use a 3mm wire, well, all else being equal, I would expect the 3mm wire cable to be more lightning resistant. But the trouble with that is, well, 4 is better than 3 and 5 is better than 4, and where do you stop? Remember all those trade-offs that we talked before. Nevertheless, there are some utilities that have adopted minimum wire sizes. The ones that I see are 2.9 to 3mm, but those are arbitrary. There's actually no basis behind them whatsoever. Just sounds good. Empirically, some utilities will cite their experience and say, well, we've used a lot of numbers, 7No8, which is 3.26mm, and we didn't have any lightning performance problems. So let's use that as our minimum wire size. And I can respect that. And those utilities don't have a lot of lightning problems with their OPGW. But remember those trade-offs. It does increase the size, weight, and cost of the cable. Material matters too. ACS performs better than AY. Galvanized wire would perform the best. Why? Because a galvanized wire is essentially 99.99% steel. An ACS wire is 90% steel if it's conventional 20.3% ACS. More steel means it's less likely for the wire to be burned through. And as a consequence of that, some utilities require an all ACS outer layer. But again, remember the trade-offs. Wire count also matters. A certain amount of energy will burn through a certain number of wires. So if I have 12 wires on the outside, say 4 wires burned through from this energy, 4 out of 12 is better than 4 out of 8, right? 4 out of 8 means I will have lost or expect to lose about 50% of my strength. Having said that, there's also a correlation with total wire count and overall wire diameter. So a 3mm wire on a cable with only 8 outer wires is not going to perform as well as that same 3mm wire on a cable with an outer layer of 12 wires. The greater arc area may effectively be spreading out the like the contact surface of the lightning strike, and therefore the cable suffers less damage than you would predict based upon the wire diameter alone. And then low footing resistance correlates with lower incidence of lightning damage. So my recommendation to a lot of customers is if you can, there are parts of the country where it's not appropriate, but if you can, put some effort into making sure you have good footing resistance. What that's going to do is make strikes more likely to hit at or near a structure where the cable has some protection from the dead ends or the suspension units that are supporting it. Plus, the structure itself will take a disproportionate number of strikes. So what about the design type? Is that important? And the answer is, yeah, a little, but you need to consider it in light of all the other factors we've discussed. So the center tube type cables are good. I think they provide acceptable lightning performance, but they tend to have lower wire counts on the outside. And remember this. Limited pipe type designs do a little bit better, and the best seems to be the stranded designs. These are rough, very rough guidelines though. So we've discussed the design types, we've discussed important design considerations, and I just want to leave you with this one slide about that in cab on our website. We do have our advanced cable engineering system for both OPGW and ADSS. And if you play around, you can learn more about optical cable design just from using our ACES system, and it will help you pick the optimal cable for your project. And I want to give a shout out to Preform Line Products because they helped us put that together. It helps you pick the accessories too, so give it a try. And that's the end of the formal presentation. So you can use the Q&A now to submit questions, and I will do my best to respond. Let me pull up the Q&A. And then did we have maybe questions in chat? Aha. Okay, wow. A lot of people tried to submit questions from chat, and it would help me out a lot if you could repeat your question in the Q&A. Oops, I've messed that up. Okay, I'll do my best to ferret them out. Okay, we have a question here. Do you have any thoughts on ground wire segmentation to reduce losses? Um, yes, I have thoughts about it. I don't like it. I don't like it. I don't like it because uh, often the analysis, I think, was flawed because the system losses were based on the use of a conventional ground wire, such as 3/8" EHS or 7 number 8. A typical OPGW will have much less resistance than one of those conventional cables that I mentioned. And so some of the savings in system loss is actually a phantom. And then secondly, the other thing I don't like is that it compromises the performance of the cable to behave as a shield wire. So you go back to, it's basically similar to a case when a line has bad footing resistance. Strikes then become more evenly distributed throughout the cable, the line, which means they can hit just as much on the cable at mid-span as they do at the towers. And so you're in a probability situation where now you've increased the probability of lightning strikes hitting the cable, and along with it, the probability of cable damage. So I'll try to type that in here so you don't like it. Um, I think the loss savings often not realized, and it compromises the shielding function of the cable. If you do it, then you need to use an aluminum pipe type design. Okay. Let's see. Next up. Wow. It's hard for me to see the questions. Oh, here we go. What did I do? Okay. I can't hit send. Okay, I can't actually, oh, there we go. Strange. All right. Ground wire segmentation. Okay. Have the folks at Center used your engineering program? I don't know. Alan, good question. Uh, I don't know. Please ask them to. Okay. All right. Um, let's see. Does Aeolian vibration affect attenuation? Does this change with each type of cable? No, it does not. Um, uh, the Aeolian vibration test is really a test um, of the hardware fittings and specifically the dead ends. That's what can sometimes cause you to fail that test. I've never actually seen an attenuation problem with a cable from either an Aeolian vibration test or a galloping test. What happens is that the cable physically breaks. Strands break from fatigue damage, or the cable itself breaks in a galloping test. If that happens in a galloping test, you've got bad hardware or a bad cable design or both. If it happens in an Aeolian vibration test, it's generally because of the dead end design. And use a different type of dead end and the problem goes away immediately. But no, I don't see the attenuation change in that test. In 96 fiber center tube designs, are there additional manufacturing design limitations other than the zero fiber strain margin? And my answer would be no, no. But need more room for all those fibers, so you could lose some fault current in making the additional room. Otherwise, you will lose zero fiber strain margin. Okay. Okay. Will in-cab offer more of these? Yes, we have a whole series. Yes, we have a whole series of these coming up. I'm being told to stop typing, so okay, I will. Yes, we have a whole series. The next one is tentatively scheduled for next week, but I think we're probably going to push it back a week. So I have additional time to prepare. But anyway, look for an email that'll give you more information about the next one. The next topic, though, is going to be OPGW 102. I will be talking about how to pick your splice points, doing your sag and tension calculations, and okay. Let me know if you can't hear me. Okay. Okay. Let's see. Well, I was asked, what's the recommended footing resistance per structure? I think the maximum should be 50 ohms. I think you really need to get lower than that, and that's, some soil conditions are not conducive to doing that. Florida Power and Light, though, I will give a shout out to. They do a really good job of doing that, and if that's of interest to you, drop me a note and I can link you up with somebody there who can tell you in detail how they do it. See, I've got some thank yous. I got we can hear you. That's good to know. I don't see any other questions. Anything else? Kind of going once, going twice. So thank you for your participation today. I always appreciate it when I get questions too at the end. And a question through chat about professional development hours. I am in the process of trying to get us registered to do professional development hours, but I think that process is going to take me at least a month. And with all the craziness going on, it might take it even more than that. But I am working on that. I forget the organization I'm working with, but we are going to do that. So, okay. How do I turn it off? Thank you for your participation, and I will be, please look out for further announcements about additional courses, and I'm open to any feedback. You can also have a copy of the presentation slides by dropping us a note at webinar@incapamerica.com. We can make the slides available. In theory, we will be making a recording of this available too, but we've had so many problems, maybe we'll do it again or something. But again, thank you all for your participation and really appreciate it. If you have further questions or something, feel free to reach out to me. Thanks again. Take care.